Now it is.
Now you are? Okay, so this is 8th period, Friday, 3rd period. You're watching this. I'm sorry to give you yet another video, but I wasn't here yesterday. I was home. It was terrible. So, everyone, smile instead of straight and look nice. Oh yeah, you can do some looking at the crowd shots too if you want to get creative.
The eager crowd.
If I give them any time to do some whatever. All right. So, John Park, you look great.
Thank you.
All right, let's go over homework kind of briefly. There were 2 related rates problems, 31 and 37. Let's do just one of those. Which one would you like to do? 37. Okay. I think I even know this problem by heart by now. 37 is kind of an interesting sort of engineering kind of problem. The picture is something like this. And there's some kind of I'm not sure I'm using the correct word for this object, but there's some kind of piston or something like that. And there is a metal bar attached to these 2 guys. There's a metal bar attached to these 2 guys, and what is happening is that this object is, well, let's just read the problem. Let's see what it says. The endpoints of a movable rod of length 1 meter have coordinates x, 0, and 0y. So figure the position of the end of the rod on the x-axis is, and then they give you the function. X of t is 1/2 sine pi over 6t. Okay, so this is very interesting. This is very different from the previous related rates problems we've done, because now they're giving you an explicit formula for the x variable over time. Problem, or we're good?
No, we're good.
We're good? Okay. And if these people's heads are in the way, just let me know and we'll tell them to go away.
Will do.
So what's happening, if they're giving me the x position, then how I'm interpreting this problem is, this guy is the one which is moving. Or what you can imagine is that there's some kind of engine or something attached to this piston, or I might be using the wrong word, but whatever you want to call it, and it's moving left and right. And as it's moving left and right, it's along this kind of axis, it's attached to this metal bar, and as it moves in towards the center, it pushes the bar up, and which pushes this other piston up. And then as it moves back out again, it pulls the bar down, and it moves this guy down. And so what's happening is horizontal motion is causing sort of vertical motion. This is sort of a way, this represents a way of sort of transferring horizontal motion to a sort of in a perpendicular direction. All right, they ask you a bunch of questions. First off, find the time of 1 complete cycle of the rod. Well, let's see, what's happening? Well, let's say it starts, well, I can plug in time 0. Where am I when t equals 0? When t equals 0, I'm here. And then it's a sine function, right? So that means at first x is going to get bigger. So x gets bigger, and then it goes back again, and then it goes, and then sine becomes negative, and then it goes back again. So 1 complete cycle of this piston is just, it just goes, and then that's a complete cycle. How long does that take? Well, it's simply the period of this function. And the period of this function, using pre-calc knowledge, is just 2 pi over that number, so it's just 12 seconds. So it takes 12 seconds for this whole thing to repeat. Again, that's just getting you to think about the problem. And then there was another kind of introductory question, which was also just there to get you to sort of think about the problem, which said, what is the lowest point reached by the end of the rod on the y-axis? All right, so when does this rod, when does this piston go, how far down does it go? What's its lowest point? Well, y will be lowest whenever x is biggest, right? And what is the biggest value of x? 1/2. It's just the period of this function. So if the biggest value of x is 1/2, I can make a little side picture. If this is 1/2, then this is just going to be root 3 over 2 by whatever, 3690 triangle ratios. So y will be root 3 over 2. Okay, that was kind of just the warm-up. Now the actual math question. It says find the speed of the y-axis endpoint when the x-axis endpoint is 1/4. Okay, so what we want is the speed of the y-axis endpoint, in other words dy dt, when the x-axis endpoint is at 1/4. So when x equals 1/4. So what is dy dt when x equals 1/4? Okay, let's do it. So read and understand the problem. Draw a picture. Pick variables for the quantities which are changing. Well, they told me that this is x0, so that's really like saying that that quantity is x and that quantity is y. Add those variables to your picture. Rephrase the information given in the problem. Write down what it is that we're looking for. Seek a relationship between the variables. Well, the obvious relationship between the variables is x squared plus y squared equals 1. Okay, and now I want to know what dy dt is, so I'm just going to differentiate. So I get 2x dx dt plus 2y dy dt equals 0, and then I can solve for dy dt. It's negative x dx dt over y. Okay, but this problem is a little bit more complicated because, sure, I've solved this in general now, but I need to figure out not what dy dt is in general, but what is dy dt when x equals 1/4. Okay, so in other words, I need to figure out, okay, so we'll just keep writing this. What is x when x is 1/4? It's just 1/4. So I get negative 1/4 times, but this is a little confusing, right? I need to know what dx dt is when x is 1/4. So I'll just leave it like that for now. And then what is y when x is 1/4? Okay, well for that I can make a little picture again. So if that's 1/4 and that's 1, again the cool way to do this is to say, to try to just make it all integers. So if I make that a 1 and I make that a 4, then you can kind of just do this in your head because that's like root 16, so then this is like, this is just root 15. So then divide everything back through again by 4, so the answer is just root 15 over 4. So y is root 15 over 4. Okay, so really, finishing this problem just comes down to figuring out what is dx dt when x is 1/4. Everybody following this so far? All right. Well, what is dx dt when x is 1/4? Well, they give me an explicit formula for x. So since they give me this, I can just differentiate. So let's just take the derivative of x with respect to time, just like a regular derivative problem. So it's going to be 1/2 times derivative of sine of something is cosine of the something back inside for the derivative of the something. So that's like another pi over 6. Okay, so now I have my formula for dx dt. Dx dt is just pi over 12 cosine pi over 6t. All right. And now I want to know what is dx dt when x is 1/4. But if you sort of think about what's going on here, well, that's not what this formula is telling me. This formula is telling me what dx dt is at some particular t value. But I don't know, I can't just plug in like 1/4 here. That doesn't make any sense. So before I can finish this, I need to solve like a kind of a separate problem. And the separate problem I need to solve is, you know, what, at what time t is x equal to 1/4? Someone see what I'm talking about? If I can figure out at what time x is 1/4, then I can plug that into the derivative formula to figure out what the speed of x is when x is 1/4. Okay, so I can do that, I guess. I just need to set x equal to 1/4 and then solve for t. So now I need to solve the equation 1/2 sine pi over 6t equals 1/4. All right, this is just a little bit of pre-calc here. So that's like sine, is this making sense? sine pi over 6t is 1/2. I don't know how Giles did this, but the way I teach it, I sort of say to myself, if sine of something is 1/2, then that something must be, when is sine 1/2? Sine's 1/2 at pi over 6 and 5 pi over 6. So pi over 6 plus 2k pi and 5 pi over 6 plus 2k pi. Those are the two times when that happens. And then to finish solving out the equation, I just multiply both sides by 6 over pi. So that's going to give me 1 plus 12k and 5 plus 12k. Okay, in other words, this is going to happen, x is going to be at 1/4 when t is 1 or 5. Let's see if that actually makes sense. Well, since the period of this function is 12, I guess it's going to start here at time 0, and then I know sine function, sine goes kind of up, then down, then down, then up. So I'm going to be here at time 3, back here at time 6, here at time 9, back here at time 12. So that does seem right, that x will be 1/4. If that's 1/2 at biggest, then I'm going to pass the 1/4 mark after about a second. That sounds about right. Then I'm here at time 3, and I pass back again at time 5, and then I'm back to 0 at time 6. So it's looking pretty good. So now that I know that that's true, now I can evaluate this. What is dx dt when x is 1/4? Well, it's just pi over 12 cosine of, well, I'm just plugging 1 in here. So cosine pi over 6 is root 3 over 2. So I get pi root 3 over 24 for dx dt when x is 1/4. I can also try it. I can also try plugging in 5. What if I plug it? So I just concluded that dx dt was I just concluded that dx dt at t equals 1 is pi root 3 over 24. What is dx dt at t equals 5? Well, if I plug cosine 5 pi over 6, that's negative root 3 over 2. So I get the opposite. But I think it doesn't matter because in the problem they said find the speed of the y-axis endpoint. So anytime people use the word speed, that's a keyword. That's not to be ignored. They don't use that word lightly. If they mean velocity, they'll say velocity. If they mean speed, they mean speed. So therefore, what they're basically saying to you is, you know, signs are irrelevant. So that way we can just use either one. Everybody with me? All right, so now finally, plugging it in back into this formula, I now know what that number is. The 4's cancel, so I get negative 1 over root 15 times the speed at x is 1/4, which is pi root 3 over 24. And now simplifying and ignoring the negative, I think the root 3, you can take a root 3 out of the top and the bottom. So it's like pi over 24 root 5. And they told me last period that they rationalized in the book. So if you multiply that by root 5, it's pi root 5 over 120. And the units are meters per second. Okay, cool? How much? Cool? Alright, good. Let's do more problems. So I'm probably going to give you like 2 more related rates problems, like ever, and then I'll just call you experts on this. Alright, there were other problems from the other section. So page 216, it was like 1, 4, 7, 19, 24, 25, 44, 50, 65, 66, 69, and 71. Let's do a couple of these. I picked out a couple. I don't know. Do you have ones you want to do?
71.
71. We can do that. I think 69. Was that the bicycle problem? No, 65 is the bicycle problem. Thought we could do like 50.
How about 66?
Yeah, maybe do that also.
You think I would just like draw like a random graph of
Oh, yeah.
characters?
Well, 66 though was hard.
66.
Yeah. Okay, I might do that one also. Let's do like one more. Let's do like 44. Cool. So 44. This was not really a hard problem. 44 said, okay, it's a mean value theorem problem. It gave you some function, and it said, find the values of C which satisfy the mean value theorem. So here was the function. It was x cubed minus x squared minus 2x on the interval -1, 1. Okay, so is the mean value theorem applicable? Yeah, of course, because it is a polynomial. Polynomials are continuous and differentiable everywhere. So what does the mean value theorem say? The mean value theorem says that there exists a C on the interval -1, 1 such that the derivative at C is equal to f of 1 minus f of -1 over 1 minus -1. Okay, let's figure out what those things are. What is f of -1? If I plug it in, I get 0. -1 minus 1 is -2 plus 2 is 0, right? Right?
Yeah.
Your crappy enthusiasm is being recorded for posterity. What's f of 1? 1 minus 1, just -2, right?
Yeah.
Yeah, okay, cool. So this says find when the derivative is -2 over 2. So basically, we need to find, according to the mean value theorem, there's some place on this interval where the derivative is exactly -1. Okay, well you just do that, right? So take the derivative, it's 3x squared minus 2x minus 2. Does that factor? Wait, something's weird. No, nothing's weird. Is this right? Yeah. Okay. No.
Yeah, and then it equals -1.
Oh yeah. Oh man. Yeah. So that's the derivative, and I want to see when is the derivative equal to -1. So now I just solved this equation. So 3x squared minus 2x. Add 1 to both sides, and now I think it factors hopefully nicely. 3x squared. Yeah, it has to, right? 3x squared minus, yeah. So the answer is when x is -1/3 or 1. Okay, but 1 is just like the right endpoint, so that's just like blah blah. So really, that is the number. That is the number on the interval -1, 1, where the slope of the tangent line equals the slope of the secant line. Are we cool? Okay, let's do another one. Let's do. Whoa,
Hold on.
good catch. You have to like turn around. And also, what's up? Yeah. Move your chair, like, like turn around. Yeah, good. What you doing, man? All right. So let's do 50. That was another even. It was like some trig was involved. But I don't know. Do you want to do this or just move on? Let's move on. Let's move on. So let's do 65. This problem was very interesting. So 65 is about 2 bicyclists. So 2 bicyclists begin a race at 8. This is exactly like the example I was giving in class last time. 2 bicyclists begin a race at 8 a.m. They both finish the race 2 hours and 15 minutes later. Prove that at some time during the race, the bicyclists are traveling at the same velocity. Okay, let's do it. So, we're going to make a picture. And let's call x equals 0, 8 a.m. 2 hours and 15 minutes, that's like 2¼ hours, that's like 9/4 or whatever. So this is like time on the x-axis in hours. And let's suppose that the race is like 100 kilometers. Because bicyclists, they can go like about 50 kilometers an hour. Yeah, faster. For a short race. All right. So there are two bicyclists. Let's draw some pictures of their possible paths. Well, one of them, they both started at the same place and they both ended the race at the same time also. So maybe one guy kind of went like that. But maybe the other guy kind of started off slower, but then he caught up at the end. So some kind of situation like that is going on. All right. How do I do this problem? Prove that, what do I have to prove? Prove that there was some point at which they were going at the same time. Ingrid, what do we do?
You create a function that's
Oh, I was hoping you'd give me the wrong answer first. Yes, that's right. Okay, this worked out so perfectly. Fourth period. So here's what not to do. This is what about 30% of students do, and this is actually incorrect. You could just try to jump right into the mean value theorem. So what does the mean value theorem say? The mean value theorem says that there's a point somewhere on this interval where they're going at the average speed. So we could draw that line. The red line represents the path of the person who is going at a constant speed the entire way. So the mean value theorem says that there exists a point on this interval where the instantaneous rate of change equals the average rate of change. In other words, it says that there's some point such that the person is going at exactly equal to the average rate of change. And it also says that there exists some point, let's give these guys names. Let's call this guy on top, let's call him F, and let's call him G. So these are the functions which represent the positions, the position of the bikers over time. Well, the mean value theorem says that there exists a point somewhere on this interval between 0 and 9/4 where the tangent line to the g function is also parallel to the secant line. Okay, but though that's true, everything I just said is perfectly correct. That does not actually, raise your hand if you did this. Yeah, I feel like it's usually like half the class, or like maybe you guys are just really smart. If you did this, that's actually just not correct. Because the theorem said, or the problem said, find a point where they're going at the same speed. All this shows is that there are two different times at which they're both going at the average speed. But these times are not at the same time, right? Those are two different times that they're going at the speed. You have to show that there's a time when they're going at the same speed. Okay, Ingrid. Now the correct answer. Sorry, I doubted you.
Find the derivative of their difference.
Yeah, you do that same thing over again. You construct a new function, which is, just like she said a second ago, you construct a new function, which is the difference between these two functions. And then you note that, of course, they start the race at the same time. So h of 0 is 0. And they also end the race at the same time. So h of 9/4 is also 0. And then, what exactly do we do now? Yeah, we apply Rolle's theorem. So we apply Rolle's theorem to h on the interval 0, 9/4. Assuming that their positions are continuous and differentiable, then the difference of those two functions is also continuous and differentiable, and there we have some function h such that the y value is the same at the left and right endpoints. And you know what goes up must come down. So there must exist a place, says Rolle's theorem, on that interval where the derivative is 0. So according to Rolle's theorem, there exists a c on the interval 0, 9/4 such that h prime of c is 0. But what is h prime of x? H prime of x is just f prime of x minus g prime of x. And so h prime of c is f prime of c minus g prime of c, and if that's 0, we've just shown that f prime of c equals g prime of c. So that was our objective, to show that there exists some moment c at which the speed of two particles is exactly the same. Alright, everyone cool? Alright, 66 is kind of just a dumb problem. I really don't want to do it. Do I have to? Do you want me to?
No, don't do it.
On a scale of 1 to 10, how interested are you? Whatever? Not? Okay, let's just skip it. 71, should we do 71? This is almost, 71 is almost exactly like what we did in class. It was x to the 5th plus x cubed plus x plus 1 equals 0. Use the intermediate value theorem and Rolle's theorem to prove that the equation has exactly one real solution. So this is exactly like what we did in class, right? Show that this has exactly one solution. Well, showing that it has exactly one solution is really like two things. It's showing that it has a solution and then showing that it has only one. So to show that it has a solution, you just mess around with some numbers like, I think -1 works, right? -1 and 0. So f of -1 is like -1, -1, and 1, so it's -2, and f of 0 is 1. And thus, this function looks like at -1, it's here at -2, and at 0, it's up here at 1. So it must cross. The x-axis somewhere between -1 and 0. So you just say that, right? This function is a polynomial, so it's continuous everywhere, and 0 is a y value between f of -1, thank you, and f of 0. F of 0 is 1, and f of -1 is -2, so 0 is between -2 and 1. So by the intermediate value theorem, there exists a point C on the interval -1, 0, such that f of c is 0. It crosses somewhere. All right, that tells me that we have at least one root. So f has at least one root. And now I have to show that it has exactly one root, so I have to show that it can't have two. So suppose it has two, suppose f has two roots. Is this coming back to you now? This is exactly what we did in class. Yeah. Suppose f has two roots. Well, if f has two roots, then that means that there are two numbers, a and b, for which the function is 0. So f of a equals f of b equals 0. Well, now Rolle's theorem is then applicable to this function on this interval. So by Rolle's theorem, there exists a point C on the interval AB such that f prime of C is 0. That sounds fine until you look at the function, and when you differentiate this function, you get 5x to the 4th plus 3x squared plus 1. And this function is always positive. So we have the assumption that there were two distinct roots led me to the conclusion that there's some place where the derivative is 0, yet I just showed that the derivative is always positive. That's a contradiction. So my assumption that there are two roots is false, so there are not two, but there's at least one, so there's exactly one. Alright. Good. Any other questions from this homework? I thought it was okay, right? No Fang, you satisfied? Alright. Melvin, you alright?
Yeah.
Long week, boring, just got all the homework? Let's move on to something else.
Yeah, okay.
Can I have this homework? Everyone, please? Right.